Assalamu alaikum. I welcome all of you to the video lecture series on basic concepts of chemistry. Today we will be discussing Sp hybridization. So without wasting time, let's start. Previously we discussed the sp3 hybridization and sp2 hybridization. So before this video, in the previous video I gave you some problems to solve, and after that I solved that in the previous video. So today we'll be discussing sp hybridization. So I will not be going into so much detail because it is already discussed in another form, just like in sp2 and sp3 hybridization. So what is sp hybridization? Here in this case, 2s orbital, 1 in quantity, and one 2p orbital, they mix together and form hybridized orbitals, 2 orbitals. Okay, 2s orbital, this is okay, 2s orbital, and a 2p orbital. I am writing it a little bit high in energy. They mix together and produces 2 hybridized sp hybridized orbitals like these. So what will be the energies of those orbitals? As in the previous lectures, I've just assigned some values to the 2p orbitals and the 2s orbital. Okay, so again we need to extrapolate those values. Those values are not scientific values, but they are just there to make you understand that what is the relation between the hybridized orbitals and the p orbital or the s orbitals which are unhybridized. So it's just showing the energy comparison, okay, and also between the sp3, sp2 and sp hybridized orbitals. Okay, so as I assigned the values to s orbital as 10, it was assigned a value of 10, energy value of 10 without any unit, because we don't need any unit, and another random value of 12 because 12 is more than 10, so the p orbitals are a little bit higher in energy. So when those two mix and produce those two averaged orbitals, okay, weighted averaged orbital, what will be their energy and to whom its energy will be near? Okay, so as 12 plus 10, it is equal to 22, and divided by 2, because we have got 2, we mix 2, so it's an average, so we'll get 11. Okay, so previously as we did this for sp3 hybridized orbitals, okay, each sp3 hybridized orbital gave the value of 11.5. sp2 hybridized orbitals, they gave the value of 11.3, and suppose this sp hybridized orbital, it gave a value of 11.0. So why these values? Because they have no scientific backing or anything else. These are just the values to make you understand the relationship between these orbitals, that which orbitals are of higher energy, hybridized orbitals are of higher energy, and which are of lower. So sp3 is higher in energy, sp2 is a little bit lower or moderate in energy, and sp is lower in energy. But to which thing we are comparing them to? So we are comparing them to s orbital, 2s orbital and 2p orbital. Okay, so this is 2p orbital, which we assigned a value of 12 energy. I should write it a little bit up. And 2s orbital, which was assigned a value of 10. Okay, So as you see that 11.5 sp3 hybridized orbital, because it has also the 3 p orbitals combined together, high energy, they are 3 in quantity and 1 s, so their average come out to be 11.5. 11.5 is near to the 12. Then sp2 has a value of 11.3, so it is again a little bit near to the 12, and sp hybridized orbital has a value of 11. Okay, so we can write it like this. Energy values, so a little bit comparison, because this is the last video on sp hybridization or simple hybridization. So it is here the sp3 hybridization. This is energy. Okay, energy is moving up, energy is increasing upward. I should write it here. So this is for energy, the arrow. Energy is moving up. Now sp3 has this energy, as we saw, it is 11.5. Now another orbital, these are hybridized orbitals energy, okay, each one. So sp2 hybridized orbital has an energy of 11.3, and sp hybridized orbital has a value of 11. sp has 11.0. okay. So I just wanted to compare them. Okay, so the lower energy of the sp, the middle energies of the sp2, and the higher energy of the sp3. Why I am so much stressing or repeating the energy words? Because these are the energies which will you will be able to which will make us able to understand the reactivities of those molecules which has sp3 hybridized orbitals, sp2 hybridized orbitals or bonds, and sp hybridized orbital or bonds. Okay, these are the things which will make us understand many concepts. Okay, so let's go to the sp hybridized orbital. So the first thing we got is its shape and energy. Okay, so its shape is like this. So again we need to compare it to the shapes of the sp3 orbital. The sp3 orbital has a shape of this. This lobe is bigger. sp2 orbital has a shape with a little bit smaller lobe and a little bit bigger this thing. And sp hybridized orbital, it has this very smaller in compared to the other. Okay, as you know that this is the lobe which makes bonds, so in comparison to the other, this lobe is bigger for the sp hybridized orbital and those are smaller. It's not that you can't say that it's larger, you can just say that it has more overlap area available. Okay, take it in that sense. So this is smaller, this is a little bit bigger, because this lobe doesn't contribute to the bond, this lobe contributes to the bond. So you can say that the strongest bond will be found by the sp hybridized orbitals. Okay, so suppose CH3 and this is 1H, this is sp3 hybridized orbitals between C and H, and this one is sp hybridized, sp2 hybridized orbital making bond with the hydrogen, and here it is sp hybridized orbital which is making bond with the carbon. Okay, so let me write it in a little bit original type of way. These bonds are lengthy, these bonds are a little small, these are very small, but you might be saying that I just already told you that this is more extended outward. This doesn't mean that the orbital itself is very large. It means that a large electron density can be converted, is present here. Okay, in this thing, then that one and that one. What is electron density? Density mean mass per unit volume, or now here we will say the electron cloud per area. So here the electron cloud per area is much more than this one and this one, so it will make strongest of the bonds. Okay, this is the energy. So again in the next step let's come that how they would arrange themselves in space according to the Vesper theory you might have heard. Or you can say that how sp2 orbitals arrange themselves in a space. So they arrange themselves at 180-degree angles. Okay, this is one orbital, it will be arranged like this. Okay, and the other one will be arranged like this. This is a little bigger, this is smaller, but both of them are the same size. Okay, but so anything which makes a bond with those orbitals should be at 180 degrees with each other. Okay, but now when we go to the carbon, okay, this is all what we are discussing. I was discussing carbon atom. Okay, so let's move again to the carbon atom. As you know that this is 2s and 2p orbital. In the ground state it looks like this. Okay, but now when an excitation takes place, this one electron move upward. It could be a px, py, pg, so don't worry about those. Okay, now what happens in sp2 hybridization? These two orbital mix together and form a bond. So these two make a bond. Okay, and those two px or py's, or you can say this is pz, py, px, py, pz, this is px, this is py, pz. One, two, you don't worry about those things. Okay, two of the p orbitals are left unhybridized, and the one of them is hybridized. Again, you will be thinking that why are not those two remaining and they are not hybridized? Please understand, try to understand. I would like to make you understand once again or repeat that statement. Hybridization just tell you that how bonds could be formed. Okay, right now we are just talking about a carbon atom. Or ultimately you will see that which molecules have the sp hybridized orbitals or has sp bonds. So we are talking about those. Suppose it in a carbon, this is its electronic configuration. So what is there now? You have those two orbitals, but what about the p? So here energy play a little bit role. As you see, these two orbitals, they have this energy. As I told you that it is 11.0, but two p orbitals which are perpendicular to each other, they remain unhybridized. Okay, but they have the energy of 12. Now the two things, the hybrid orbitals, they just arrange themselves like hybridized, sp hybridized orbital in a carbon atom arrange themselves like this. One carbon, suppose we are talking about one carbon, one will be both of them will be pointing at 180 angle to each other. Okay, this is the place where a bond can be formed. Okay, this is the tip of this orbital, and now here this is the tip of this, which can overlap with a hydrogen or anything to form a bond. So this thing is a little bit clear, but what about those things and what are their function? One thing is why they are left behind. We are not right here discussing the term why they are left behind, because hybridization is a process which just tells you that how a covalent bond or the shape of molecule may look like, and how it also explains to somehow the bond lengths and the energies of the bonds in a molecule. So it just tells about the shape and lengths and angles between the atoms. Okay, so again there might be some other molecule which have some experimental values. So let me write that molecule. So today we will be explaining this we will be discussing this molecule. This is called as ethine or acetylene, or you can say ethine. Okay, and this is its nomenclature, and we shall study it. But one thing we now studied, that we have two or hybridized orbitals which are pointing in the opposite direction to each other. So this here thing can also form a bond with anything this place, because each one has one electron present in it. And okay, it can form, it can share its one electron with any other atom which want to share with it, and this can share with them. But what about those things and how where they would be present? Okay, so let's look at now. We would like to focus on the structure of acetylene in order to understand the sp hybridization and where those p are put together, okay, and where will be the sp hybridized orbitals. Okay, so we are discussing this structure because its experimental values are known. They say that those two hydrogen are at 180 angle to each other. It is experimentally determined. Okay, so hybridization is going to prove that how it is possible. Okay, now this is the molecule, and we need a proof of this through hybridization, that this structure, or we need to justify this structure by using hybridization. So one thing is clear, that it has hydrogen and hydrogens, and for sake of simplicity we may say that only carbon is hybridized. Those carbons hybridizes, okay, and hydrogen uses just its one s orbital for bonding. It is not hybridized, though it is again in some advanced courses you can say that what's actually which orbitals this hydrogen shares, but for right now we say that this is 1s of hydrogen, and this is the hybridized orbital of carbon. It is linked, it is the hybridized orbital of carbon, and it is the 1s of hydrogen which is linked. So as you know that 1s orbital has one electron present, and this hybridized orbital has one electron present, so they overlap and a bond is formed. Here a bond is formed. So let me write it a little bit clean way. This is our carbon, this is another carbon. Okay, now it has a sp hybridized orbital. This is a sp hybridized, this is present on the carbon atom. Okay, okay, actually suppose this is, okay, I am writing it in a little bit different way, you will never understand it by that. Okay, let's see it. This is one. Now it has another orbital sp hybridized which is pointing outward. Okay, now this is a carbon atom which is sp hybridized. This is another carbon atom which is sp hybridized. We just are discussing this thing, that how it would be formed. Now there are two other orbitals. Let me write it with the green, because when sp hybridization takes place, two sp hybridized orbitals are formed, and both the hybridized orbitals are pointing in opposite direction. So this for each carbon. Okay, this is one, it is pointing here, and let me write the other one on a red. It is pointing toward inside. Okay, now this thing, this has one orbital as a black, and the other I am going to write it with a green pen. I will try that it should be visible. Both of them are now overlapping with each other. This is one and this is the other. This is one lobe and this is the other lobe. This is the carbon. So for drawing a lobe, I should write the carbon a little bit away. What I have drawn, this is carbon, this is carbon, this is outer orbital, this is outer orbital. Now we just have produced what? This thing. Okay, carbon, I have written carbon there, this carbon I have written there, this bond with sp hybridized orbital. But there are two other hydrogen atoms, there are two other orbitals remaining which need to form a bond. And this orbital, it forms a bond with a hydrogen 1s orbital. Okay, hydrogen 1s orbital. As you know, hydrogen has one electron and it has one electron present in it, so it shares. Okay, here again this red one has one electron present in it and the blue one has again one electron present in it, so it is shared and a bond is formed. This is a bond. Okay, and what we have done or added, we just added another bond to it. It is a hydrogen bond, CH bond with an sp hybridized orbital. Now the other one is, I tried it again, a CH bond with hybridized sp bond, hybridized sp. Okay, so this is sp hybridized bond, this is sp hybridized bond, but where are the p's? They are left there. Okay, but as you know that atom is very small and all the things are almost very much near each other, they sort of overlap over each other. So this is the direction of the bond. So what will be the direction of the p orbital? As I okay, so the p orbitals should be perpendicular to this plane. Okay, so it is very easy. One p orbital should be like this and the other p should be like this and they will overlap. Okay, perpendicular mean at 90 angle, this thing and this is 90 angle, both the black, it should overlap. Okay, here to here it will overlap and bond is produced. Okay, this is one black p orbital and this is other black p orbital. They have one electron each in them, but okay, and now they overlap with each other. This is just like alkene, and very well, it is very good that this thing overlap. But remember, there were two orbitals. What about the next orbital? How would it overlap? So now a skeleton is a little bit modified. The other orbital should be perpendicular to this axis. This is called a sigma bond axis because this is the line for sigma bond. Okay, or you can say this is x axis, so the sigma bond is on x axis, this is y axis, so two orbitals are on y axis. Okay, what about the two other orbitals? Because this carbon has one p left with one electron present in it and this has another one p left, so both of them are at so both of them should be perpendicular to this thing, the bond axis, the sigma bond axis, and also to the other two p orbitals, because you know the p orbitals in a molecule are perpendicular to each other. All the three p are arranged like this. Okay, so you utilize that one, but the other two are like this. Okay, the other two are left behind. Or suppose you utilize this one. Okay, now two are left, one is pointing toward you and half toward you and half here, the other is half above, half below. So okay, these are left behind. And if you want to do with this structure, as you know, the p orbitals, this is a p orbital, the other p orbital is perpendicular to this one and the other p orbital is perpendicular to this one. Okay, so let's see, this p orbital is in a plane. Okay, so this is used in hybridization. Now you have left two with you. The upper one, this one, it produces a bond with other one, other p which was in its direction, and another which is here in this direction. It should form a bond with the other. It will be clear to you with a little bit models. Okay, okay, now this thing, look at this thing. What is this? Suppose this is look at this, these are, suppose these are two carbons, the black one carbons, the red one hydrogens. Okay, so black one are carbons and the red ones are hydrogens. They have formed a bond. Okay, so let me write this thing with a blue or something else. I am writing that thing. Okay, now this is our molecule. Now I am holding it like this. Okay, this is carbon, black one, this is the other carbon, this red one is hydrogen and this red one is hydrogen, so I am writing like this. Okay, what about those p orbitals? Thank God that I have 2 ball points. Okay, now these are the 2 orbitals perpendicular to each other. They can overlap, laterally mean sidewise. Okay, one electron present here, one electron is present here, so they weakly overlap with each other on the above or on the below side, because the electron is in motion. Sometimes its electron is here, sometimes it is here, sometimes its electron is here and it is here, and there are 2 electrons and both are in opposite direction, because it is the requirement for bond that both the electrons should be not like this, it should be paired. This thing is called paired, this is called parallel. Those should not be parallel, they should be paired. Okay, so these are the p orbitals, they overlap with each other, but 2 other orbitals are remaining. Okay, what to do with them? They should be arranged in such a way that they should be perpendicular to this plane, the sigma plane, and they should be perpendicular to the pi plane. This is pi, this is this p, which has bond of 1,5 pi bond with this. Okay, now there are 2 p orbital remaining, one on each carbon. This is one and this is the other one. Okay, so this is the structure. Those 2 will overlap with each other because each one has a bond. So this is the actual structure of acetylene. This is the structure of acetylene, or the acetylene look like this. These 2 p orbitals, they are perpendicular to each other, so they are independent of each other. They are not forming bond with each other. Those 2 are in the same plane or in the same direction, so they can make bond. Those 2 can make bond. So I should write it on a board like this. The upper one are very easy. The yellow one, the up one, I should write it like this. They can form a bond with each other. They have 1 electron each. Now the one coming toward you, I should write it, because it is not possible to write on a board like this. So there is one thing which I can do. This is the way they are written. Okay, these are the blue ball point right now. They are those. So they overlap with blue, overlap with the blue, and the yellow overlap with the yellow. These are the yellow one, they overlap with each other. These are the blue one, they overlap with each other, and each has 1 electron in it. This has 1 electron, this is 1 electron. Okay, so how the overlap take place? Okay, so this is the molecule as an example, and we need to tell that what is the hybridization of this carbon and this carbon. Okay, so very easily we can tell the hybridization of this one, because it has formed 1, 2, 3. This I should write it with the blue. That is a sigma bond, and these are sigma bonds, so it is sp hybridized orbital. So this is sp2 hybridized carbon, because it formed 3 sigma bond and a 1 pi bond. But this thing, it formed 1 sigma, other sigma, 1 pi. I don't know what this is. Okay, and how to explain this? It seems like sp2 hybridized orbital, but before looking to it, we need to go into a little bit detail of this thing. Okay, what is the detail? Suppose, first of all, let's assume that this molecule is formed from this molecule, C, X, H, NH, and another H. Okay, what will happen now? Suppose, as you know, that there are 2 electrons present in this bond. All bonds, this is sp2 bond, sp2 bond, sp2, sp2 bond, and this X somehow take away both electrons with itself. Okay, and run away. So when it run away, so a positive charge will appear. This is the positive charge which is here. Okay, so immediately we say that how the s orbital, this was sp squared or sp2 orbital which was forming a bond. So I am explaining this thing. Okay, so first of we need to focus on this thing. So suppose, look at this thing, it has to form a bond like this. This is sp orbital, and the other one, the red one, is of X. This is X, okay, and there are 2 electrons in it, and they are shared between those atoms. One is with S and the other is with the one is of this carbon and the other is of the X, and it is a covalent bond which is formed by the sharing of the electrons. Okay, now what happens? The X went away, the X ran away, it took the electrons, but it did not take the orbital with itself, with it, but it take an electron from this orbital. Now this orbital is sp2, but this is empty, so a positive charge will appear on the molecule. Okay, because what will happen now, this molecule or this molecule, this and this molecule are almost the same. Okay, so I am explaining this one. So what will happen there now, and this is very important orbital, sp hybridized orbital. Okay, now what the molecule will say, it doesn't have electron, so it should, the sp hybridized orbital, as you know, that is very low in energy. This molecule this is sp2 hybridized orbital, and sp2 hybridized orbital is very much lower in energy than sp3 hybridized orbital. So what this molecule has its own mind, and it is very sharp. It will do one thing, it will quickly take back, this carbon will take back the s character from this orbital and rehybridize. So this orbital is deleted, the molecule will rehybridize to sp. Now why to sp? Because you know that the energy of the sp, this is sp2 and this is sp. sp has lower energy and is more stable, so this will immediately go to sp. But there are 2 things associated with the sp. One thing is the sp has a requirement that it form bonds, this carbon will form bond with in this way. Okay, there should be 2 sp orbital. Let me write it like this. Okay, these are 2 sp orbitals. One will form bond, suppose with anything like this, with H, and the other is forming a bond with H in this fashion. Okay, but this thing is bent. Okay, this thing is bent. What will happen when it changes to sp? Now this is not more bent, it will form a bond with hydrogen. But what happens, it came from sp2 to sp, so what thing appears, and other p orbital is developed, because sp2 has 2 p orbital, p has 1, so it kick out 1 p orbital from sp hybridized orbital. Okay, and now become sp, because sp is stable. This molecule is very greedy, it wants to be stable. Okay, so it becomes stable, and as you know, with the stability, what will happen, these are the sigma bonds, and it will be like this, so it becomes straight, the molecule will be straight. So this is sp. Okay, and how it would look like, this molecule will never be like this, it will be in a straight direction, because you know that sp has a demand of planar molecule or a linear molecule, just like you saw C triple bond C H and H, because it cannot be bent. If someone write it like this, it is wrong, because those orbitals are like this, straight at 180 degree. So this is the correct form. So this will be sp. So this thing has a hybridization of sp. This is sp2, and this is the molecule, the positive charge. Okay, so this is one example, and I'm going to give you some other examples in the question in the problem set. Thank you very much.